So it says record lesson. We are going to record the lesson. Kirchhoff's laws, and that is pronounced Kirchhoff. The nice thing is, if we're analyzing circuits, these are the rules for analyzing circuits. There's two main ways to do this. One, you can do this mathematically. This is how I was taught in university. Everything came as a system of equations. In fact, you usually ended up with 2 or 3 different systems of equations, and you solve them, and it works great. But there's a more intuitive way that I've stolen from my friend Mr. Kreitsch that involves treating every circuit as a ski hill. And Owen, there are 2 rules. There are 2 Kirchhoff laws. There's a voltage law and a current law. And Nicole, I'm going to abbreviate Kirchhoff's current law as KCL quite often. You don't need to well, you're not going to need to know which law is which. You don't need to know how to apply them. Here's what Kirchhoff's current law is. It comes out of the idea of conservation of charge. On an electrical level, protons and electrons can't magically vanish. That would require matter to disappear, and that's not allowed. In my ski hill analogy, the number of skiers you start with has to be the number of skiers you finish with. You're not allowed to have skiers go missing. That's not a functional model for a mountain. In English, it says this: at a junction between wires, current flow splits or combines and continues to flow, in air quotes, downhill, the direction the positives would move if they could. When the current splits or combines, no charge is lost, so the total flow into the junction equals the total flow out of the junction. I'm going to give you the mathematical version of it first, but I'm going to give you the more intuitive version. The mathematical version says this: the total, the symbol for total is the summation symbol. Current in has to equal the total current out. The sum of all the currents coming in has to equal the sum of all the currents coming out. In my ski hill analogy, it says this: here I have 2 amps coming in. Here I have 1 amp coming in. Well, how many amps must flow out, Owen? Yep, that's the current law. And it is usually that easy. You're going to hear me say, when I'm solving a circuit, if I can figure out the total current leaving the chairlift battery, the question's going to fall apart. So as a strategy, and we're eventually going to list this, but I'm going to start building it right now, I'm going to bend my efforts if I'm solving a circuit to try and figure out the total current. So it's going to look like this. Example 1 says, find the unknown currents. Carly, you and I are going to go skiing together. I'm going to zoom in a little bit. First thing I'm going to do is identify where the battery is. See it? Bottom left corner there. The positive is the long bar. The negative is the short bar. Now, in real life, don't write this down. In real life, In real life, electrons flow in that direction. Don't write this down. We don't want to have stuff going uphill. It's too confusing. So even though negatives in real life move in that direction, we're going to pretend that the positive moves in this direction. So everybody, as soon as you see the chairlift, label downhill and put a letter I there. Now, I've put the arrows on the rest of the circuit for you, Carly. If they weren't there, first thing I always do is I walk around the circuit labeling downhill. It's a cheap trick because also, Owen, I'm seeing how the circuit is put together while I'm doing that. It'd be like before you go skiing, you look at the map of the mountain. Okay. Carly, how many amps right here? You said it, you thought it right and read it wrong. Try again. How many amps right here? Same answer. How many amps right here? How many amps are leaving the chairlift battery? How many amps are leaving in this circuit? If I know that, the question's going to fall apart, but I would identify that first if I could. In fact, I'm just going to write that in. I know that the current is 1.75 amps, and now I'm going to start to ski downhill. So, Carly, let's go downhill, which I know is up the page for a bit. Use your imagination. It's all downhill from here. How many amps? How many amps going through this resistor? How many amps right here? This has a question mark next to it. How many amps? If I put an ammeter there, I would measure 1.75 amps. How many amps going along the bottom row here? And it's almost going to be that easy. It is going to get tougher because we're going to have things splitting up and rejoining, but it's almost that easy. Nicole, you and I are going to go skiing on the next one. First thing we're going to do is we're going to label downhill. Nicole, see the battery? Which way is downhill? Up the page or down the page? The longer one is the positive. So everybody, put a little arrow there, put a little arrow there. Notice right here we split up. Let's keep going to the right. So this is downhill. This is downhill. Which way is downhill in this section, Nicole? To the left or to the right? I think your icon here. Yep. Ooh. And which way is downhill in this section here? To the left or to the right? If they hadn't put those arrows there, I would have put them in. That's also the direction I'm going to move my eyes as I go around this circuit. All right. How many amps right here? How many amps right here? How many amps right here? How many amps are leaving the chairlift? Because I know the number of amps leaving the chairlift, trust me, the battery, the question's going to fall apart. Okay, so now let's start to ski. I might even write a little note to myself, 3 amps. Often I'll call that I total. The total current in this circuit is 3 amps. It can split up and rejoin, but it can't get above or below 3 amps. So you ready, Nicole? How many amps right here? Right here? How many amps went down this ski run? How many amps are left over to go here? You can probably do it in your head. If not, use a calculator. What are you going to do? Tell me out loud what you're going to do to calculate it. More specific, what minus what? You're correct. Go with what you think. You're right. You're going to go 3 minus 0.8, which is what, folks? Has to be. I'm not allowed to lose skiers, so I know this is 2.2 amps right there. Let's keep skiing on this outer run, Nicole. How many amps right here? How many amps going through this resistor? I would measure 2.2 amps. How many? Oh, here. How many amps right here? How many amps right here? Well, notice the 0.8 went straight down. 2.2 amps came this way. How many amps right here? Yes. Now, my ski hill analogy, Ethan, breaks down a little bit. What's 0.8 of a skier? Yeah, we're going to have decimals. But we can pretend what really happened is right here, the skiers all shook hands. 0.8 of them went down this ski hill. 2.2 of them went down this ski hill. And then they all met up at the bottom of each ski run at the same height and kept going. That's going to be our analogy. All I can do now is put more junctions and more split ups, more forks in the road, and more rejoins. Example 2 says, show the direction of each current and then find the unknown currents. Nathan, you and I are going to start. I see the ski hill in the left-hand corner. I'm going to label downhill, downhill. And I would strongly encourage you, take the 1 second to do that. Much like I won't help you if you don't do a free body diagram. If you haven't labeled downhill, I'm walking away. Nathan, it looks like that's downhill and to the right is downhill at that junction. Down is downhill and to the right is downhill. If I follow this one all the way around, along the bottom, downhill is to the left. Along the bottom, downhill is to the left. Along the bottom, downhill is to the left. Nathan, do I know how many amps that are leaving the chairlift? Nathan, do I know how many amps are leaving the chairlift? Yes. Figure it out. Follow it, follow it, follow it. How many amps went this way? How many amps went what? Has to be 13. Has to be 13. I must have started with 13. This is Kirchhoff's current law. Current cannot vanish. It can split up and recombine. It can't vanish. How many amps? This question's going to fall apart. Let's ski along the top run. So right here, skiers shook hands. 8 amps went down this way. 5 amps said, we're going to go down this hill. Oh, right here, they split up and shook hands again. How many amps went down here? Leaving? Yep. How many amps went through this resistor? 3 amps. How many amps went through this resistor? 2 amps. Let's follow. Ooh, how many amps would I measure if I clamped an ammeter around that wire? Yep. How many amps would I measure if I clamped an ammeter around this chunk of wire? Yes. Good. How many amps will I measure at the bottom of the chairlift? I'm going to rephrase that. How many amps must I measure at the bottom of the chairlift? Got to be 13. Okay. Do another one. Brett, let's go skiing. Oh, there's the battery. So I guess downhill in the bottom row is to the right. Here we split up into 3 sections. That's downhill, that's downhill, that's downhill. They recombine, that's downhill. Along the top row, downhill is to the left. Looks like they split up. Those are downhill, and then they recombine. I can see how this fits together. Brett, do I know how many amps are leaving the battery chairlift? Sorry? How many? How did you figure that out? You're correct. Yeah, there's a spot where everybody rejoined. All the skiers went through this hill, and we must have had a little counter there, someone with a gate counting the skiers as they went by. 5 amps there. That is the total current. So this has to be 5 amps. And again, Matthew, the fact that I know the total current leaving the battery, this question is going to fall apart. As soon as I got that number, no matter how tough the circuit, I relaxed because I said, now it's just going to be meticulous and being careful. Okay, how many amps right here, Brett? How many amps went this way? How many amps went this way? Leaving. Yep. Then they all recombined. Yes, they did. There's the 5 amps. How many amps over here? Gotta be. Is that okay, Nicole? This is the ski hill. This is the Kirchhoff's current law. I'm going to say skiers can't vanish. Whoever leaves the chairlift has to make it back to the bottom of the chairlift. We're not going to have like search and rescue here. They all make it back alive. It breaks down because decimals, but you know, it's still a good analogy. Okay. Downhill is going to be this way, this way, this way, this way, this way, this way. That take 1 second, do that. I strongly encourage it because you see how it all fits together. Ethan, do I know how many amps are leaving the battery chairlift? Oh, great. I usually, if there's not a slot there, I again often just draw it there as my security blanket, as I know how many skiers are coming off the chairlift. This question's going to fall apart. I'm going to start to give you less and less hints as we go on. So how many amps right here? How many amps here? How do you know? 1 amp went down this way. So let's continue skiing the outer run. 3.5. How many amps going through this resistor? Has to be. Oh, how many amps down here? Yep. Oh, how about this blank here? How many amps? Got to be 1 amp because there's no junctions between them. They'll have the same current. How many amps right here? And hey, we matched our leaving the chairlift. Is that okay? Next page. Mr. Dueck, what affects the current? The resistors. This next little blurb here is handy. You can survive without it, but sometimes it'll give you a shortcut. So I wrote the amount of flow, the number of skiers, the current, along a particular path depends on the resistance. How wide or narrow the ski hill is. Of course it does. So if the resistance of each path leading away from the junction is the same, what can be said about the splitting of the current? It says, find the unknown currents below. So each resistor is R. In our magic idea of a ski hill, what we're saying is the 2 ski hills are identical. If the 2 ski hills, if you come to a fork, if the skiers come to a fork and both ski hills coming up are identical, what would make sense for how the current splits up? 50-50. Yeah. It's going to be 3 amps, 3 amps. That shortcut I'll use sometimes. I might notice, oh, there's a 10 ohm resistor and a 10 ohm resistor. I can just split the current without having to do any math. If one has more resistance, so big resistance, think skinny, narrow trail, I'm telling you, I2 is going to be smaller than I1. Big resistance, you can't get as many skiers on it. B, that's a handy error check when you're looking at your numbers, but you can survive without it. The one you can really survive without is C. It's convenient. but I've never had to solve a circuit just with that. It says if you happen to notice that they're simple ratios of the resistors are ratios of each other, the current will be ratios of each other. So Alexis, how big is the first resistor? Capital letter what? How big is the second resistor? Twice as big, half the skiers. So how can you take 6 amps and break it up so that twice as many skiers go here than here? How many skiers here? How many skiers here? How many amps here? How many amps here? If I want this to be half as big as that. 4 and 2. I have never had to use that to solve a circuit. But I imagine if I was an electrician, I'd be using shortcuts like that all the time. That's the current law. Skiers split up, they recombine. Groups split up, they recombine, but your total leaving the chairlift has to be the total at the bottom as well. Voltage law is a little bit trickier. I'll abbreviate Kirchhoff's voltage law as KVL. It comes out of conservation of energy, GG, because voltage is the amount of energy per coulomb. It also means that, well, here's what it says. As charges flow around a circuit, they experience voltage gains from the battery chairlift and voltage drops around the resistors. For every path through the circuit, the voltage gains equal the voltage losses. In math speak, which I will never write, in fact, I don't even know if I put these on the math versions on your formula sheet, it would say this: the sum of all the volts that you gain has to equal the sum of all the volts that you lose. What did I say voltage was like? Starts with letter H. It's like height. I'm going to treat it like height. Here's what this really means in English. Look, if you're skiing, if the chairlift gives you 200 meters of height, you have to lose 200 meters to get to the bottom of the chairlift. You can't lose 199. You haven't got to the bottom of the chairlift. You can't lose 201. But past the chairlift, that's impossible. Whatever you gain from the chairlift will be what you lose going through the circuit. And so as long as you're always skiing downhill, if you start with a 12-volt battery, do you know how many volts you're going to lose going through the circuit? 12 volts in total. So in my ski hill analogy, Kirchhoff's voltage law says if the chairlift takes you to the top of the mountain, you have to lose the height, the voltage you gain from the top of the mountain. So let's suppose we have a battery and it is a 12-volt battery. Here is our battery, 12 volts. And you go through 2 ski hills, 2 resistors. If you lose 8 volts going through this resistor, how many volts must you lose going through the second resistor? Has to be. Has to be. That's Kirchhoff's law for current. So it's not current is, for voltage. Not voltage is conserved. It's whatever you gain, you got to lose. Energy can't gain or lose. It's really a conservation of energy. Whatever you start with, you finish with. So example 1. I'm going to start out labeling everywhere in the circuit, and then we're going to get lazy in a few examples, and we're going to say, here's what we're going to label. But for now, let's start doing some skiing here. Peyton, ski with me. Let's start, first of all, before we even jump in, let's label downhill. So downhill, 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 downhill. This is the direction I'm going to move my eyes as I move through this circuit. I've said to you that the battery is like the chairlift, voltage is like height. How many volts are we gaining going through the battery? How many volts must we lose by the time we get to the bottom? Same answer. Okay, so how many volts high are we right now? Say it. So right now, coming off the chairlift, all the charges are 20 volts high. Have we gone down a ski run yet? Say no. How high are we right here then still? More specific as a number, how high are we still here in volts? Okay. So in my ski hill analogy, this is the flat section after the chairlift that you're pushing yourself with your poles to get to the top of the first hill. Here's your first hill. You and I are going to ski down it together. Whee! How many volts did we lose going down this first hill? Leaving. We go down another hill. Whee! I don't know how high that hill was, and I'm not sure. Well, wait a minute. How high are we here? How high are we here? How high are we here? How many volts must we have lost going through this resistor if we started at 12 and ended at 0? That's the voltage law. Ooh, this one's got, why is that dark there? Is yours dark on your printout? Okay. These diagrams, oh, you know what? Maybe it's not there. That was just something weird. Okay. These diagrams are getting a little bit old. Let me make this 200 size. First thing I'm going to do, Ronan, is label downhill. Everybody find the battery, label downhill. Downhill, downhill. To the right is downhill along the top, and downhill is to the left along the bottom. Ronan, how many volts am I gaining from the battery? So how many volts high are the charges right here? This one's a little harder than Peyton's. Everybody splits up here. There's a fork. Okay. Do you want to ski the inner run or do you want to ski the outer run? Doesn't matter, pick. Okay, if we did the inner one, how high are we still? We haven't gone on anything. We're still 10 volts high, yes? Whee! I don't know how high I am. Wait. How high am I right here? How high am I right here? How high am I at the bottom of this hill? How many volts did I lose going through the hill? Some people went to the right, this way. How high are they at the top of this hill still? They were 10 volts because they haven't lost any. Whee! This also got them to the bottom. Sorry, not 10 volts, Mr. Dueck. At the bottom, they're 0 volts high. How many volts did they lose going through this resistor? Now, this bugs students because students are going to say, Mr. Dueck, I have a 10-volt battery and I got 20 volts out of it. No. Any complete ski run was 10 volts, as long as you're always skiing downhill. Let's do a couple more. All I can do is add more forks and more ski runs, more resistors and more junctions in electric speak. Faith, let's go skiing together, you and I. First thing we're going to do is label downhill. There's the battery. Downhill is up on the left. Downhill is to the right along the top. Downhill is down here. And then along the bottom, downhill is to the left. How many volts are we gaining from the chairlift? So everybody starts out, all the skiers, all the current, all the amps start out 12 volts high, and everyone goes down this first hill. How many volts do they lose? Leaving? So right here, we're 4 volts. In fact, now we split up, but at the top of each hill after we split up, we're all still 4 volts high. Do you want to ski the middle run or do you want to ski the outer run? I don't care, pick. Okay, in the outer run, how high are we here? Whee! We went down this ski run, and this got me, oh, you know what? I think this got me down to the bottom, yes? So how many volts do I lose going through this ski run? Has to be. What about in the middle? Well, we started out 4 volts high. We went down this ski hill, whee, and we ended up at the bottom. Megan really likes the little wee sound. Okay, I'll keep doing that. I know my audience. How many volts must we have lost going through this resistor? And again, this bugs kids because Alexis, I'll have kids say, but Mr. Dueck, 8 plus 4 plus 4, that's 16 volts from a 12 volt. No. That's not what I'm saying. I'm saying any path adds to gains 12, loses 12. There's one path. There's another path. Gains 12, loses 12. Now, do I have one more? No, good. We're labeling everything. Eventually, we're going to just label the battery and the resistors because and we're going to label the chairlift and the ski runs. That's really what we don't need to label the flat areas. But Owen, let's do one together. So 60-volt battery, pretty big battery. Downhill this way, this way, this way, this way, this way, this way. Right? How many volts are we starting off with from the battery? So right here, we're 60 volts high. Everyone goes down this ski run. What do we lose going through this ski run? And why is it a loss? Because remember, voltage is energy per coulomb. We're bleeding energy off through a resistor. That's a light bulb or your smartphone or whatever. So leaving how many volts? Right here, I'm 45 volts high. Right here, I'm 45 volts high. Now, what if I tried doing the outside run? How high am I right here? How much do I lose? Leaving. How much do I lose? Okay, I can't ski the outside run yet. I have to do the middle run because this one here, I have to fill this in before I can fill these in. I don't know how high we were because we all joined together. Owen, look up. We all rejoined, met here, but I don't know how high they were. So let's ski down this one. How high? What do we all lose going through this ski run? Well, we lose 18, leaving. Good. How high are we when we join together? How high are we right here? How high are we right here? Thank you, Owen. How many volts do we lose? Well, wait a minute. How high are we right here? 0. You know what? We lost 27 volts going through here. Let's now backtrack to that other ski run. How high are we right here? Well, first of all, how high are we right here? How high, Owen? How high are we right here? Ready? How high are we here? 45. What do we lose? Leaving. How many volts must I have lost going through this one? YouTube's going to be wondering what goes on in my class. I wonder the same thing sometimes, YouTube. To me, labeling everything, though, really clutters things up. To me, I'm going to start to label the resistors and the battery, and then I'll just do the math in my head. And if I need to use a calculator, Nicole, I'll use a calculator. And again, I've told you on a test, I'll do 1 + 1 on a calculator because I've made so many dumb mistakes. I'll try and do a little bit of math in my head sometimes in my homework. By the way, 2 very useful conclusions. Owen, from here to here, how many volts? Because this is where they split up, this is where they met up. From here to here, how many volts in total? Because this is where they split up and this is where they met up. If you happen to notice that 2 chunks of ski hill split up and met up, even if one chunk is made up of multiple hills, those multiple hills everyone has to go through the same voltage drop. Has to. That can be a nice way to fill in some missing gaps. So this says 2 useful conclusions. For any complete loop, the voltage gains equal the voltage drops, but also no matter which way you go between 2 points, the drop must be the same. Owen said, hey, this is 18 volts, this is going to be 18 volts, because if we start here and end here, and we lose 18 there, start here and end here, we're going to lose a total of 18 here. That last one, I hope you picked up on. That can be really, really, really handy when you're trying to find missing stuff. So what you're often going to hear me say is, you're stuck, go back to the beginning, start skiing again, ski a different path. It says, to see this relationship, it's sometimes helpful at first to redraw the circuit so that all the resistors are pointing downhill. I disagree with this. I've left this in out of respect to my friend who typed up these notes. He teaches at Kwantlen, and I really do respect his teaching, and I've heard good stuff about him. But so he says he teaches his students to redraw this circuit like this. Everyone look up. Everyone look up. Everyone goes on the chairlift. Everyone goes through this hill. That's R1. And then they split up. And yes, mathematically, those are identical. I'm lazy but organized. I don't want to have to get in the habit of redrawing every circuit. I'm going to tell you, get used to just kind of imagining that this is that without redrawing it. So 5B could be redrawn. The one that Owen and I and Brett did could be redrawn as really big chairlift. Everyone goes down to 15 volts. Then we split up. Oh, this was a big steep hill of 18. The better skiers went on that one. I'm not that good a skier. I'll do a 10-volt hill followed by an 8-volt hill. I'll do it in chunks, but we all lost 18 volts, and then we rejoined and all went down the last one together. Does that make sense? That's how you can think about circuits as ski runs. Example 6 says write equation. Nah, we're not going to bother. Next page. So if you have several ski runs in a row along the same path, each ski run will use up some of the height, except what am I referring to as height? Starts letter V? Voltage. So here's an example. We have a 30-volt ski chairlift. Each resistor is identical, which means each of them has the same height. How many volts do you lose going through each one then? 15. By the way, the current would be the same in each of them as well, because are there any junctions? No. So what's the current going through here? I. What's the current going through here? I. What's Ohm's law? It's on your formula sheet. What does V equal what times what? You can do this purely algebraically. They have the same I, they have the same R, they must have the same V. They have the same I, they have the same R, they must have the same V. And the only way that works is they're 15 each. If the resistances are not the same, okay, big R means small I. Small r means, oh, no, wait a minute. That doesn't work. Sorry. So this is going to go on YouTube as a dumb mistake by Mr. Dueck. Are there any junctions in this ski run here? No. Then you know how many amps are leaving here? I. Amps. You know how many amps are going along the top run, Ethan? I. Amps. You know how many amps are going through big R? Little r? You know what? Big resistance, same current. Bigger V, smaller v. In other words, V1 is going to be greater than V2. You can survive fine without that. I will give you some algebraic questions, but I'll usually tell you, hey, just make up some numbers and crunch it, although I'll show you how to solve stuff algebraically too. Nathan, if you notice they're simple ratios of each other, notice this resistor is twice as big as this resistor, twice as skinny as this resistor. Okay, Mr. Dueck, the voltages are going to be in a 2-to-1 ratio. This is going to be 20 volts. This is going to be 10 volts. I've never had to use that to solve a question. I have had to use this top one. Oh, if the resistors are the same, I know the voltage will be the same. Let's put it all together. I like example 8, I like example 8, I like example... Actually, although this is going to sound weird, example 8, too easy. But we're going to start here. I would consider this a C- level. I wrote, although it's helpful at first to label voltages everywhere, from now on, we're going to label the chairlift, we're going to label what's coming out of the chairlift, and the ski run, the resistors. Example 8 says, find the unknown voltage drops, currents, resistances, and power loss. V equals I times R, and also power equals V times I. Now you're going to start to hear me say, if I know 2 things, I know 4 things. In fact, the dumb joke I make here, the dumb memory trick, I'll say, knock, 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 knock. I know 2 things, I know 4 things. You ready? Jet, let's ski together. Here's our circuit. Let's first of all label downhill. Downhill, downhill. Looks like downhill is down in the actual circuit, and along the bottom, downhill is to the left. First thing I want to do is the current law. If I can find the total current flowing through a circuit, the question's going to fall apart. Do I know how many amps are coming out of here? How? You're right. Talk to me. How many amps right here? How many amps right here? How many amps right here? There's no junctions. How many amps leaving the battery? I'm telling you, this question's going to fall apart. We're going to fill in all of the currents. Then we'll fill in all of the voltages. Then we'll knock, knock. Who's there? I know 2 things. I know 4 things. How many amps right here, Jet? They split up. How many amps went this way? How many amps went this way? I've done all the currents. Now let's ski. How many volts do I gain coming off of this chairlift? How many did I lose going through this resistor? Leaving? Good. Whee! Did that get me to the bottom of the chairlift? How many volts must I have lost going through there? Knock, knock. I know two things. I can now find all four things. I'll do that as my last step. Let's ski the other one. How many? Oh, 18 minus 6. We're 12 volts high here. Whee! How many volts did I lose going through here? And I could do that two ways. I could do that by skiing all the way to the bottom of the chairlift, or I could have said, you know what? If they split up and met up, each group must have lost the same voltage, the same height. Now, I know two things. I know it said find the unknown voltage drops. I've got the V's everywhere. Find the unknown currents. I've got the currents. Oh, resistances. What's Ohm's law? Everybody get your calculators out, please, in your hands. Resistances. What's Ohm's law? It's in brackets. Get the R by itself. Tell me as an equation, what divided by what? So here, find the resistance. Go V divided by I. What's the resistance? Is it 1.5? Can't be hard. What's the resistance? 6 divided by 4? I think I said 6 divided by 5. 6 divided by 4. What? Good. What are the units for resistance? Someone hasn't done much homework at ohms. Okay, here, knock, knock. I know two things. I can find the resistance. It's going to be V divided by R in your head. V divided by I, 12 divided by 3 in your head. This one's going to be a 4 ohm resistor. In your head. In your head, what's the resistance here? We're finding all the missing resistors, then we're going to find all the missing power. Someone hasn't done home. Okay. Volt. By the way, stupid organized, lazy organized. Check, check, check. What's the last thing it wants me to find? What's Joule's law? We just wrote it on there. Without a calculator, V times I. How many watts? 6 times 4, baby. Without a calculator, V times I. 12 times 3. How many watts? 36. Without a calculator, 12 times 1. Okay. I will not give you this question. Here's what I would consider fair game. If I said to you, each resistor is a light bulb, which bulb is brighter? The top one, the middle one, or the right one? My mom says I'm not the brightest bulb. Jet, she means something different. Trust me. Which light bulb is the brightest bulb? The top one, the middle one, or the right one? Which one? Why? What's its power? That's not the top one. The top one would be the one on the top. Oh, the middle one? The one that I called the middle one because it was in the middle? That one there? Yeah. So often what I will do is I won't tell you, solve the circuit. I'll say, what's the brightest bulb? My mom said, I know some of you that's going to bring some emotional pain. But there you go. Shaz, you got to do better. Okay? I'm coming to you because, man. Oh. Let's label downhill. Okay. Here we go. How many amps? How'd you figure that out? Oh, I got 1 this way, 1.5 that way. The only way that works is if I had 2.5 coming in. Current is always what we try and find first. How many amps went this way? Yep. 1. How many amps went this way? I got all the currents that I need. Good. Now let's see if we can do the ski trick. Voltages. How many volts did I start with? How many volts do I lose here? In your head leaving? So, whee! Oh, how many volts must I lose here? And then I got a choice for the second one. I can start here and ski, and it's going to be 14. Or I can realize, Matthew, if we split up and if we meet up, if we lose 14 going this way, we lost 14 going this way. Knock, knock. I know two things. Now I can find resistance and power. Resistance is V divided by I. I'll let you use a calculator for this one. Power equals V times I, 21 times 2.5. Or I squared R, or V squared over R. I got lots of options. Resistance is V divided by I in your head without a calculator. Power is V times I in your head without a calculator. Good. Resistance is V divided by I, 14 divided by 1.5. Is it repeating? So I'll go 9.33. I need to move over just a smidge. Ohms. And power is going to be V times I, 21. Jet, what's the brightest bulb in this picture? The top one, the middle one, or the right-hand one? Hey, this time it was the top one. That was actually the one on the top. I'd probably call it R1, R2, R3, or RA, RB, RC. Yes. Because right now I'm being pretty casual and I'm going to probably use my answer button, sure. Because usually what I'll do is I won't solve. I'll probably figure out what's the last thing you're going to find. In this case, it was going to be either this power or this resistor. And I would have said, find that, knowing you had to find all the other stuff first. To give you context, this is about a C level. They're going to get tougher. Don't panic, though. You've learned the method. Now it's just practice. Yes? Sorry? Oh, wrong units. Thank you. And catch me on that. I have the terrible bad habit of putting the wrong units in, and I'll try and beat it out of me again. But if I'm not concentrating, I'm always half a step ahead of you, trying to go to where I'm going next. Catch me and correct me on the units. Thank you. I will be fussy on units, ironically. Alexis, let's go skiing. Okay. What am I going to do first? Label downhill. Now, you're going to find out, and you may have sensed this already, to me, I find solving circuits like addictive Sudoku puzzles. This is like popcorn. Once I get a few of these, I just start diving right in. So you're going to see I really love solving these. I find them nice little brain teasers. So let's ski. Can I figure out how many volts right here? So you're saying this ski hill, I lose all of my height, and that means everyone's on the ground now? That's what you're telling me. How many volts am I gaining from the battery? 40. So you're telling me I lose all 40 volts here, and I'm at the bottom. What? How did you figure that out? You kept going with your eyes, and you realized, well, that hill, 35, got me to the ground, and that means this ski run, which is a legitimate ski run because it's always going downhill, has to add to 40. Yeah, you know what? That leaves only 5 volts. This must have been a pretty small hill. By the way, Mr. Dueck, how come you didn't start with current? Good question. I should have mentioned that. I did. I went, okay, I don't know how many amps here. How many amps here? How many amps here? Don't know. So, okay, then next I go skiing. How many volts? How many volts? Whee! How many volts? And I could have done that the way I just showed you, or I might have already seen, you know what, if we're splitting up and meeting up, this hill and this hill have to lose the same same height. Knock, knock. I do know two things. Where? Here, but even more important, here, I can find the current. V equals I times R, get the I by itself. So it's going to be 35 divided by 5. How many amps? Why does that help me so much? How many amps? 8. Knock, knock. I know two things. Now, do I know at least things on everything? I'm done. Now it's Ohm's law and Joule's law. Try these on your own. I'll do them up here. Find the resistance, find the current, find the voltage, find the power. You should have 4 things on every single resistor. Do this in your head, Mr. Oh, for Pete's sakes, really? Okay. So, what did I just hit, Mr. Dueck? R, it's going to be V, it's going to be 5 over 8.625. And power is going to be 40 watts. Oh, this one's easy. Even Jet could do this. Oh, this one I got 3 things. That makes it really easy. It's going to be 35 times 7. It's going to be 210 plus 35, 200. See if you get what I got. I might have made a mistake. 5 divided by 8. Is 5 divided by 8 not 0.625? I think it is. Oh, had me worried. What did I get wrong? Bad units? Units again. I did amps again. Jeez, Dueck. Get in the habit of checking your units. And did you screw up somewhere else too? I got ohms there. Okay, wow. Whew. So this is why I said to you the other day, if you're comfortable rewriting V equals I times R in all its different forms and P equals V times I in all its different forms, and if you can do that going straight to your calculator without writing out the numbers, I'm good with that, because otherwise it just gets really cluttered. There will be ones where we will have to show work, and I'll show you how we'll do that, but they're going to be a much higher level of difficulty. There. Is that right? I got 0.625 ohms, 40 watts, 35 watts, 35 ohms, 35 volts. I already did that. 7 amps, already did 245 watts. And you know what? I was going to say the right-hand one is the brightest bulb. I'll bet you that's not a light bulb. 245 watts, that's something else. Right? Typically, light bulbs max out at about, sorry, you can get massive light bulbs. Stage lights, for example, are much brighter, much more wattage than that. But all right, let's do another one. These are fun, Mr. Dueck. What did you do in school today, Arnica? I went skiing. You know what, Arnica? Let's ski together, you and I. First thing we're going to do is label downhill. Wow, she gave me a pretty good stink eye there. She didn't even bother sitting up or nothing. She didn't even bother sitting up or no. Oh, she did sit up now. Okay. Check for current first, Arnica. So do oh, how many amps right here? How many amps leaving the battery? Same answer. This question is going to fall apart. Let's do the current first then. How many amps went this way? How many amps went this way? Don't know. Or do I? Knock, knock. I know 2 things. I can find the current. They gave me V, they gave me R. If V equals I times R, get the I by itself. How many amps went down that path? What are you going to type into your calculator? I want this current right here. They gave me volts, they gave me resistance. I don't know, it's V equals I times R. By the way, and I'm not making fun of you, this is one of those, every time I turn the page, if I don't have my formula sheet, I write V equals IR and P equals VI at the top, because then I can just see it. And by the way, you said, is it R divided by V? Is it? It's not. So you said, is it R divided by V? No, it's V divided by R, right? Oh, I think you thought it right, but you said it backwards. What'd you say? 15 divided by 5 is not 5. Which one number are we talking about? Sesame is brought to you today by number what? How many amps were leaving the chairlift? No, how many amps were leaving the chairlift? How many amps went this way? How many amps went this way? Okay. Oh, how many amps in the bottom here? You'll get it. Yes. Well done. Oh, knock, knock. I know two things at the bottom. The voltage is going to be handy. Let's find the voltage. That's just going to be I times R. You can probably even do it in your head. It's 5 times 4. Okay. I filled in current everywhere I can. I filled in that voltage because it was just staring at me, I times R. Now let's ski. How many volts did we gain from the chairlift? How many volts do I lose going through here? Don't know. How many volts did I lose going through here? How many volts did I lose going through here? Did that get me to the ground? That means that this plus this have to add to 70. Get your calculator out. How can I figure out what the missing voltage is? Start with 70. Type 70 in. Start with 70. And then what, folks? Minus the 15, minus the 20, tells me what this has to be to get to 0. How many volts must that be? Knock, knock. I know two things. I can now find all 4. I'll come back to that. Let's keep skiing. How many amps? How many volts? 35. How many do we start with? How many do we lose going through here? Leaving. 35. Oh, wait a minute. Look, Arnica. Did we split up and meet up this run and this run? How many volts did this ski hill use up? How many volts must this ski hill have used up? Psst. No need to do any calculator work. If we split up and meet up, the only way that works is if we start on the same height of the mountain and finish on the same height of the mountain. Otherwise, that's physically impossible. How many volts did these people lose? How many volts must these people have lost? That's the voltage law. I gave you a tougher one. Don't feel bad. Look at all 3 resistors. Do I know at least 2 things? Then I can find 4 things. Go to it. I'll do it up here as well. R, this one's going to be 7 ohms. Power is going to be 35 times 5. That's going to be 175 watts. Get my units correct. Here, power is going to be 15 times 3, 45 watts. Here, R is going to be 7.5 ohms. And power is going to be 30 watts. Here, oh, I got 3 things. I got all sorts of options. Well, power is going to be 100 watts. Did I make any dumb mistakes? If I did, let me know. Okay, I'm right. Thank you for your patience. I'm going a little slower and meticulous because this is such an important lesson. So I'm trying to really take my time here. Arnica, that okay? Yeah. Zainab, let's do one more together, you and I. There's a bit of a glitch. This was typed in, oh, Zaina, no B, sorry. This was typed in Word 1995 for Mac. This black line shouldn't be there. It should really be up there. But look, let's pretend it's supposed to be there just to make our life easy. Let's make downhill this way. We haven't done one with downhill going this way. So let's try that. It just moved a few years ago on its own spontaneously. And I don't have the ability to edit these anymore. Xana, you ready? So, first thing I would ask is, can I figure out total current? Do I know how many amps right here? Say no. Do I know how many amps right here? Say no. Do I know how many amps right here? Here? Okay, I always try that first. Next thing I'm going to try is, can I ski? How many volts do I gain from this battery? How many volts do I lose through this little ski hill here? Leaving. 24. So 32 take away 24. Sorry, take away 8 leaves me 24. Whee! Does that get me to the bottom? How many volts must there be here? And knock, knock, I know 2 things. Typically, as soon as I know 2 things, I want to try and find the current. How could I find the current in this resistor? Well, V equals I times R, get the I by itself. By the way, it's great that you're writing it. It is on your formula sheet, which you should have in front of you, and you should train your eyes to look there. It's going to be V divided by R, right? It's going to be 24 divided by 10, 2.4, I think, yes? Okay. Does that mean I have 2.4 amps? No, it means when we split up, 2.4 amps went this way. Some went this way. Well, wait. Okay. How many volts? Let's ski the outer run now. How many volts? Losing 8, leaving. I don't know how high this hill is, but how high was this hill? That got me to the ground. How high? Yes, I knew you'd get it. That's also 24. So really what happened is there was a big steep 24-volt hill. Some skiers went down that one. Some skiers said, nah, I'll do a 14 and a 10. But we will still meet up at the bottom because we lost the same height. Okay. Let's see. What else can we do here, Mr. Dueck? How can I figure out my current? Sorry? Oh, here. I'm so sorry. I know 2 things. I can find 3 things. I could have done this right away. Do I know V? Do I know R? What's I? I should have done this right at the beginning. Sorry, YouTube. 4 amps. My brain was going, I thought this was way easier, and somehow I was missing that. You know what? How many amps? How many went this way? How many went this way? And, because there's no junctions between them. Knock, knock. I know 2 things. So if you go 14 divided by 1.6, that's the resistance. This one I can't do in my head. 8.75? And it's going to be 10 divided by 1.6. And I could find the power, but we're running to the end of class, so I'm going to skip that. But I could go V times I, V times I, V times I, V times I. Sorry, I should have seen there was 2 things here. Knock, knock. I know 2 things. I know 4 things. It says light bulb questions are a good test of your understanding. I will probably give you a light bulb question or 2. It says the bulbs below are identical, same resistance. Which bulb is brighter? Jet, when I'm talking about the brightest bulb, my mom said no, I'm talking about the biggest wattage. Well, first of all, we can figure this out easy. They have the same R, it says that, so label them R and R. Megan, how many volts? Whee! How many volts? You looked away. Look up. How many volts? Whee! How many volts do I lose here? How many volts? Look up. How many volts do I lose here? Also 10 if I ski the outer run. Well, you know what? They have the same R. They have the same V. What else is the same then? What else is the same then? Yes, and what else is the same then? Because they were talking about brightness. Power is brightness. Those 2 bulbs will be identical. What about an example 10? Well, they have the same R because it says both bulbs are identical. How many amps leaving right here? I. How many amps going through here? I. How many amps going through here? I. You know what? Same R. Same I. What else must be the same? Same V, same power. Okay. What's your homework? I'm going to be giving you a bunch of these to practice. We do need to practice these. So you can try number 1. You can try number 2. Owen, don't give me a stink eye. You need to practice these. You can try number 3. You can try number 4. I'm going to skip number 5. 6 is good. 7 is good. 8 is good. 9 is good. 10 is good. 11 is good. 12 is good. I'm going to skip number 13. Skip number 14. Skip number 15. Skip number 16. Thank you very much for your patience as I jabbered away.